Okay, welcome back to Spain Engineering. Okay, now what I want to look at today is star and delta connections. Okay, so the three-phase windings of an AC generator may be star connected or delta as previously provided. The important relationship between phase and line currents and voltages is also shown. So let's look at this in all its glory. Okay, here you have current line and you have the voltage line. Now the voltage line is across any two phases. The voltage phase is across any phase and neutral conductor or midpoint of the transformer. Okay, and that's in star connection. Similar thing here you have in delta connection. Let's just make sure we can get it all the way up. Okay, voltage line is across again here any two phases. Your current line and your voltage phase. It's okay. I'm stopping because I'm trying to make sure that the voltage phase. Now make sure you understand the connection between in regard to the voltage phase in the delta connection. Okay, I have it in my mind, but trying to relate to you, it is something you'll need to look for and try to affirm in your own learning application or your own method of learning. Okay. I'm just wondering if I could have put in any more additional information on the delta section, but maybe not. Maybe it would then become too complicated for explanation. But do your groundwork for yourselves, okay? What I've just noticed is that I may recognize how it is done, but you may not yourselves. Okay. Right. IL equals IP. So current line equals current phase. VL equals square root of 3 times voltage phase. Okay. And that is in star. Now, delta connection, IL, current line, equals square root of 3 times current phase. Okay. VL equals VP, voltage line equals voltage phase. Okay. Let's just go a little bit. Current line equals current phase, VL equals 3, square root of 3 times VP. The square root of 3 is 1.732. You must confirm this for yourself, okay? Now continued. Now, the square root of 3, and I put in brackets, is simply a constant for three-phase circuit and has a value of 1.732. The delta connection is used for electrical power transmission because only 3 conductors are required. Delta connection is also used to connect the windings of most three-phase motors because the phase windings are perfectly balanced and therefore do not require a mutual connection. Making a star connection at the local substation has the advantage that two voltages become available. Line voltage of 400 volts between any two phases, and a phase voltage of 230 volts between line and neutral, which is connected to the star point. And the star point is here. That is your star point, okay? Okay. In any star connected system, currents flow along the lines IL through the load and return by the neutral conductor connected to the star point. In a balanced three-phase system, all currents have the same value, and when they are added up by phasor addition, we find the resultant current is zero. Okay. Therefore, no current flows in the neutral and the star point is at 0 volt. The star point of the distribution transformer is Earth because Earth is also at 0 potential. Let me make sure drop that down a bit to 1 to make sure I get everything in place. Okay, good. I can leave it there, I think. Yeah. Okay, I can leave it there, yeah. Okay. Right. A star-connected system is also called a three-phase, four-wire system and allows us to connect single-phase loads to a three-phase system. Three-phase power. We know from our single-phase alternating current theory earlier in this work, power equals VI cos theta in watts. In any balanced three-phase system, the total power is equal to 3 times the power in any one phase. Therefore, total three-phase power equals 3 Vp Ip cos theta in watts. Equation 1. Now for a star connection, Vp voltage phase equals VL over square root of 3 and IL equals IP, equation 2. Substituting equation 2 into equation 1, we have total three-phase power equals square root of 3 VL IL cos theta in watts. Okay? And we're still on delta connections, okay? Continuing from page 3, let us now consider a delta connection. Voltage phase equals voltage line equals IP equals IL over square root of 3, equation 3. Now feel free to go back to your equation if need be to see where we're at. That is in your interest. I will not be doing that, okay? But that is for you to do. Substituting equation 3 into equation 1, we have for any balanced three-phase load, total three-phase power equals square root of 3 voltage line times current line cos theta equals watts. So, a good general equation for three-phase power is power equals square root of 3 VL IL cos theta watts. Now let me do an example for you, okay? And I need to read this example. Example 1. A balanced star connected three-phase load of 10 ohms per phase is supplied from a 400 volt 50 hertz main supply at unity power factor. Unity power factor is 1. Calculate A, the phase voltage, B, the line current, and C, the total power consumed. Solution. For A, example 1, VL equals to the 3 voltage phase and IL equals IP. VL equals to the 3 VP. Now what I've done here, divide both sides by square root of 3, okay? And you see this is what I've done here. I want VP on its own, okay? Let me get a pen 1 second so I can make sure that I'm okay. So I want VP on its own. So here you can see that I've got VP here on its own after dividing both sides by square root of 3, okay? Okay, that now becomes VP equals VL over square root of 3. That now becomes this, okay? Now you need to find your own style of learning. All I can do is give you an open overview, okay? But you'll need to set that style for yourself. And here you have equals 400 over square root of 3. Now, we know that's 1.732, therefore we get a voltage of 230.9 volts. Feel free to try and do this for yourself. Make sure that it is correct. Do not hold me to it. I'm not perfect, and I make no possessions to say that I am in any shape or form. Okay, let me just make sure. Let me see if I can bring this up, make this a bit larger. Make sure that we don't have to strain our eyes to see it. Okay. Okay. And next part, we would then ask for the next stage. Let's look at the next part of it. Example 1 continues for B. IL equals IP equals VP over RP. And that will be in amps. IL equals IP equals 230.9 over 10. Now remember where we got the 10 from, equals 23.09 amps, okay? Now you need to make sure that you've got this yourselves and you can see how we got the answer, okay? For C, power equals square root of 3 VL times IL cos theta. I call it cos theta, you can call it what you like, okay? 1.732 times 400 times 23.09 times 1. Why 1? Because the power factor is 1, okay? And that is in the question. So be sure you know where you got that from. And here we have a value of 16 kilowatts. Now please check this for yourself. Make sure that I am right. I can be wrong. So simply, okay. Now here's the part 2. Let me just simply bring this down a bit so we get the question completely in. Now this is one you can do for yourself, okay? So I'm going to leave it there for a moment, let you look at it for a moment and make sure that you can apply it, okay? And I'm going to bring it upstairs slowly, okay, for you to resolve. Let's go back a little bit. Take it out of your field. Write, now put pen to paper. Write out, do not try to do it on screen. Put pen to paper, okay? Let me just drop this down a bit because I'm a little bit concerned here that it's not showing me. Oh, sorry, divide both sides by, okay, and you can see what I divided both sides by. Because we need current line, okay, and then I went on to here, current line, bringing IL on its own. I then brought this into play here, okay, and then this is your next stage part of it. Now I do this in sections. I don't give me myself one great answer, because what I found is that if I break it down into smaller chunks, it becomes easier to manage, okay, and there we are, okay. And for part B, okay, you can do that for yourself now. Don't need me to be banging my mouth now, okay. And exercise again here, we can look at exercise 3, okay, that's there, okay. Make sure you know how we got these solutions. Now example 3, three identical loads each having a resistance of 30 ohms and inductive reactance of 40 ohms are connected first in star and then in delta to a 400 volt three-phase supply. Calculate the phase currents and line currents for each connections. Okay, that's what it says. Let me go up the top, see if I miss anything. Here this is part B for delta connection. Okay, we want IP on its own. Okay, here, so we want IP on its own. Okay. Now here we have for star connection. Okay. We have the impedance, which is what AC current sees when it's traveling through a circuit. Okay. I'm just taking this to the end. I won't be tying this up. Okay. This here, you can see here, is 50 ohms. It's Z, and somewhere along the lines here, you will be asked for Z, I'm sure. Let me just pull back a bit. Okay, and here you are. Here's where the Z value has come into its own. Again, look for how it has been applied and how we got to this stage. You need to put pen to paper so that you understand the concept. Don't try to understand it from the screen. That does not work. Well, it never worked for me. So I can just only speak for myself. Okay. Okay, I hope you found this useful. Okay. And again, let me just go back up slowly, make sure that everything is in view. Thank you. Have a good day. Bye-bye.